Hello again to everybody. I hope that the inconvenience have not too much, and I wait that you are interested in our laboratory experiment. Well, now we are start with the alkali silica reaction from laboratory to on-site. The content um, of the conference is the following. Well, we have concrete the structure. This curve is applied for other type of things. For instance, electronic or industrial device, and it's not so normal to apply for concrete structures. We start with without any damage, and with the time, the properties of the structure can be decreased, and at certain type start to fail or to aging with the time. And if we can do an action about on the concrete structure, we can mitigate this action. For instance, alkali reaction. Estoy oyendo mucho ruido, Jorge, no sé si me podéis quitar. No oigo el retorno. Vale. Sigo. Ahora. When we can mitigate the damage process, we can restart the functionality of the this is the normal extend the service life of the structure. Me oigo con muchísimo retorno, Jorge. No sé si puedes hacer algo. Well, I will show you, ahora está bien. I will show you the symptoms of alkali silica reaction. There are two main groups of symptoms of alkali silica reaction that are direct or indirect. Not always the main symptom in an structure is direct. Could be that we cannot see the damage or the concrete with cracks, but we have an indirect symptom before have a damage. Before that we can see the problems in the concrete. Direct symptoms are mainly cracks on way of maps. That is, cracks inside the concrete. For instance, here we can see an aggregate and paste with gels. That is a stereomicroscopy image. The coloration around the cracks, this is a crest of a pavement in a crest of dam, and this is not the dark areas are colonized by the organic microorganisms, and the very high pH gels are surrounding the cracks, making that these microorganisms died. But we can see other indirect symptoms like open and mismatching of joints. Dam in Galicia, in the north of Spain, and we can see the open of joints. This is a ray in a crest of a dam that cracked due to the tension in the steel produced by the expansion of the concrete. And other symptom that is very usual in the dams are branching gates. It's necessary to open the rail in order to make sure the operation with these gates. Well, following the alkali silica reaction mechanism, we have three main agents to produce alkali silica reaction. We are talking all the time about alkali silica reaction because alkali carbonate is in discussion, and there are other mechanisms that is not too much, or in my experience, they are not too much well diagnosed cases. To produce alkali silica reaction, we need reactive aggregates, free alkalis. Free alkalis means available alkalis for the reaction, and water. If we remove one of these three factors, we can stop the reaction. What is most easy? The most easy is remove, more or less remove as soon as possible, or as much as possible, the water. Also, when we increase the temperature, we accelerate the reaction rate. The mechanism in opposition with sulfate attack is not well defined. This is a proposal of the mechanism that for me is one of the more complex and well explain the situation. The problem is that we have environmental in the pore solution that is high alkali content, and these are in solution. This means that OH is separate from the cation, and this OH enter to the go inside to the aggregates and penetrate with the small join with the small size cations. Later, the OH can or attack the siloxane bridge and break the channels of silicates. Sorry. Later, there are diffusion of silica from the aggregates to the cement paste that is controlled by calcium, that is a more big cation, and produce a layer of calcium close to the surface of the aggregates that is defined as the theory of double layer. The role of the portlandite contribute to the alkali silica reaction developed due to the acceleration of penetration of sodium and other cations and anions, avoid to the diffusion of the silica gels from the aggregates to the paste. In summary, there are some more ions that enter to the aggregates than the ions that can go out. In this case, the aggregate is spun half cracking, and later when we crack the aggregates, the silica gel can go out from the interface in the aggregate paste interface. Well, we can see stereomicroscopy image here. There are some aggregates completely attacked by alkalis. Here also, this is an opal, and the damage or the reaction goes from the surface to the interior. But in other case, when the aggregates have different phases and only some of them are reactives, potential reactives, we have the things that things like this. That is a vein of products of alkali silica reaction products that progress inside of the veins that have reactive material inside of the aggregates. If we see the products in the electron microscopy, here we can see the typical rosette-like crystals, but also we can see aggregate like this that are particles of quartz and between them and over them form of alkali silica reaction products. In this case, we can see that have a lot of sodium. That means that is formed because sodium is the small ion that can enter in the beginning of the reaction to the interior of the aggregate. Here we can see a backscattering electron microscopy image, and in this case we have a lot of gels, cracked gels in the interface of aggregate, that is this gray part, and the cement plates. Usually the voids are completely filled by the gels. Well, what is the evolution with the times? With the time, it's the same graphic that I put in the previous class. This means that we have a period of initiation, period of propagation, and period of attenuation when one of the reaction products are close to finalize the reaction. Usually we cannot go until here because before us as this situation we need to take some decision and remove the extractors or similar. For the same aggregate could be that we have different reaction rates. These curves are for the same type of aggregates in different parts of the dam. We can say that the concrete, at least in complex structure like dams, are the concrete are their surrounding circumstances. For the environmental ambient and loads or other issues. Well, in order to predict the evolution of with the time, a lot of different models have been developed, but one of them are more physical or mathematical models in which chi is estimated theoretically or even substituted by thermal expansion. Also, there are reaction models, but now we are combined both type of models, and we have progressed a lot in the prognosis of alkali silica reaction. The main parameters that leads the alkali silica reaction process or damage is reactive aggregates, free alkalis, water, temperature, compressive strength, and in general environmental conditions. We can see in complex structures that depending on the environmental conditions, the reaction rate is more quick or more slow, depending in the part of the structure which is the concrete, for instance in dams. Well, with respect to the reactive aggregates, we are talking about siliceous aggregates. We can have a crystalline structure, more or less linear or more complex, but well for the crystallization of these silica aggregates. In this case, most of them are not potential reactive aggregates, but also in much of them, or even in a lot of types of siliceous aggregates, we can see poor crystallization and amorphous structure. In this case, we can see this particle is the same in thin section petrography rotated, and we can see this particle, for instance, that have undulatory extinction. Sorry. This means that the particle is tension, have a lot of tension, and is reactive with the OH when the OH enter in the aggregates. Well, here we can see different ways to cracks formation of aggregates. Of cracks in the aggregates, depending on the morphology, or much more depending the composition. When we have a very homogeneous aggregate, the reaction products from the surface to the interior of the particles. But when we have some phases and only part of them are reactive, in this case, need to entrance and look for the phases, the potential reactive phases, to form silica gel. Another important thing that I want to mention in this conference is the misdiagnosis of calcite aggregates or dolomites aggregates. Much of the concrete theoretically affected by alkali carbonate or the dolomitation is a calcareous aggregate that has small particles of siliceous aggregate, a reactive siliceous aggregate. And in this case, we can have the Pessimon effect, that is, with a small quantity of a lot of reactive siliceous aggregate, we have the same behavior than other small rate aggregates that need some more quantity to have the same expansion. In dams, we have problems, specific problems with the aggregate because of the because it's necessary to take the aggregates of the area because there we need a lot of tons of aggregates in order to manufacture the concrete, and in this case we need a high quantity of these, and usually look very close to the quarries, close to the dams. Well, the second or the other factor that is very important in the alkali silica reaction joined with the water is the free alkalis. Why talk about the free alkalis? Because the cement, the alkalis of cement, we consider that are effective aggregate, effective alkali free, and all of them contribute to potential alkali silica reaction. But also some aggregates as feldspats and other particles can support or extract leaching some alkalis, contributing to the alkali silica reaction. But it's very important to take into account that not all the alkalis from the aggregates are available, because are inside of the big particles, and we never enter, the alkalis never enters to the aggregate, inside in the center of the aggregate. In this case, we need to test the aggregates in order to estimate the leaching aggregates from the leaching alkalis, sorry, from the aggregates or other constituents of the concrete, like supplementary cementitious material. Here we can see a very clear behavior when reduce the alkalis in cement. These are experimental lab tests, and when we use 1.25% of sodium equivalent or sodium oxide equivalent, we have a lot of expansion, while we reduce to the or when we use with the same aggregate low alkali cement, in the expansion is reduced with clearly. Well, we continue with free alkalis. This is the thing that I have mentioned before. Depending of the type of aggregate, we can have a lot of alkalis in the total composition, but not always the total composition, but better say never the total quantity of alkalis is removed from the aggregate. Here we can see the contribution of different first part. This is the aggregate, and this is the paste, cement paste, and we can see that first part produce alkali silica reaction products close to the interface. Also, I have mentioned before the potential extraction of supplementary cementitious material, but the contribution of these kind of materials or supplementary materials is not too much as according with experimental results. Well, in water, with respect to the water and humidity in dams, we have a special environment situation. Some of the concrete dams is saturated by water inside the dam, and depending on the capacity, maybe that you don't have permeability enough to water go out by the wall of the dam. But in any case, we have different situations. On one hand, we don't have tidal zone because the height of water is more or less the same all the time. We have saturate in water a big part of the concrete. In this case, is one of the most difficult to act on the water. That is one of the factor to increase the alkali silica reaction. We have talked before about the temperature. Here we have different experimental results with test bars exposed to different temperatures, and we can see that when we increase the temperature, the reaction rate increase significantly. This must be considered in the models to consider the potential expansion. This is one of the big problems of the dance, because we have insulation areas, wind over the sun parts of the dams, and other is in shadow and with more protected environment. And also we have a massive concrete inside of the wall. This is another very important is variable that we can take into account when the models are developed. sorry. For instance, here we can see the loads over the test device that show the free expansion produce a much more expansion than the concrete on compressive strength. For instance, 20 megapascal, 10 megapascal in blue, red 5 megapascal, and sorry, because the you can see that here we have a very expansive concrete, but when we have loads in the dam part of, for example, of the dams, the expansion is much is smaller than the upper part with free expansion. This means that this not means that the reaction, the potential reaction, is not producing, but is have a small reaction rate. In general, the environmental conditions are different, and produce different type of behavior inside or in the different part of complicated structure like dams. The main factor are compression, water, wind, isolation, temperature, taking into account that all the concrete is the same in all the structure. The same cement and the same free alkalis, the same aggregates, and the same type and quantity of water or cement water ratio. But we can find different levels or situation from the point of view of alkali-silica reaction. As a summary, we can define the more important parameters to predict the behavior at long term in dams or even in other significant structure like nuclear power plants. Also, this is another point. When we diagnose or study structure, we don't at certain time from the beginning of the construction, and we use different tools. For instance, this is American methodology using course cut by the middle and summarizing the cracks and gels and different microstructural characteristics that are ponderized to have a medium potential damage. This is not useful for compare different type of structures, but we can distinguish between different parts of the structure and see the more or less potential reactive rate in different areas of the structure. Also, in our institute, we have developed similar or with the same philosophy, the reaction rate in different parts of the concrete in different structures by studying by backscattering electron microscopy. Depending on the quantity and the localization of the products, we distinguish 6 degrees of damage from 0 when we don't have any alteration or any alkali silica product to 5. The small degree is G1, that means that we find gels only in pores, inside the pores, not filling completely the pores. And this is evolution until the massive products of alkali silica reaction in the concrete. Usually the worst situation that we can find is the G4 because in G5 is only found in laboratory with a very destroyed test samples. Well, with the time, when we start to study a dam or another structure, we have in a time TI that we don't know where is. For instance, we have a structure with 50 years old. That is very common in dams. But we don't know, we know the time, but we don't know how is the expansion rate. In which point are the expansion rate? Well, in this case, we have developed, also in other countries have other methodologies to estimate the fraction of expansive products have consumed at tea time. If we here we can see the S curve, and we don't know where are, but we can estimate this point using a methodology of extraction of aggregates and comparing with a reference. In this case, we can produce a map of a structure with different situation or reaction rate. We don't know. We can know the reactive material consumed before during the service life. And in this case, we can produce a mixed model that have into account the fraction of reaction consumed, the local tensional strength, and the characteristic of the materials, for instance, tensile strength. And with these tools, these are pictures of Principia, that is a specialist engineering in modeling. They can produce different scenarios, taking into account the progression of the alkali-silica reaction. And as conclusion, we can say that the alkali-silica reaction is influenced by different environmental conditions, loads, and other factors, but we have tools to define the different scenarios. Now we need, this is associated with the prognosis of the concrete structure. But now our work is centered in the mitigation, in the effect or the proposed methodologies to mitigate the alkali-silica reaction for a lot of structure that we have constructed from the 60 or 50 years old. And this all my contribution to this class today. Thank you.